Okay.
All right, so for the last talk of this mini conference, we have Denis Nardin, who is talking about, I guess, the motive. Oh, the title looks different.
Yeah.
Motive of the Hilbert scheme of infinite dimensional affine space, or something related.
And changed it because there's been, as you know, a change recently. But so this talk is going to be slightly different from the one described in the abstract, because during the weekend math has happened, and I want to give to the people here a more up-to-date version of events. But hopefully it will be interesting, even if it's a bit in progress. It's going to be a little bit more less polished than I'd like, but this is the feeling of good math, I think. So Maria has already told us how that the Hilbert scheme of points is a very important scheme. So let's actually introduce who this is. So let's start by saying what the Hilbert scheme of points. And then I know that I'm going to get complaints because apparently when people say the Hilbert scheme of points, they refer to the Hilbert scheme of points in a curve or something like that. I'm going to talk only about affine space, but let me give a general definition. So let's say S is a base scheme. It's going to be not necessarily a field. S is an S scheme, which is sufficiently nice. Let me say quasi-projective, although I think you can be much more general than that. And then Hilb X over S is the S scheme representing the following functor, sending an S scheme T to the collection of all closed subschemes of the base change of X to T, such that Y is proper of finite presentation over T. And this finite presentation is actually kind of crucial, but so is proper. And so there is a theorem that I think is due to Grothendieck.
Forgot the flat.
Oh, flat. Thank you. Sorry. Do non-flat schemes exist? Yeah, okay, yeah, they do. There's a theorem due to Grothendieck. This functor is representable, say if X is quasi-projective, much more generally indeed, but we are not going to be interested in very general objects. We're going to be interested in Hilb ANS, which is the Hilbert scheme of affine space over S. And in this case, you can see that this is the properness assumption. So now if you have Y in A and T proper over T, this implies automatically that I is finite. So you can think of Hilb AN as the scheme that parameterizes collections of points in affine space. Now this is possibly a misleading picture because the points are not just points. So for example, when you have a double point, you also remember the tangent vector. As everyone that has done some scheme theory knows finite schemes that have nilpotents. Okay, sorry, I didn't write long enough. And my screen share died, but it should have reappeared now. Okay, you have schemes with nilpotents that remember additional information. So here, the AN is not what I think is called the Chow variety, by which I mean the disjoint union over D of sim dan, of the distfold symmetric power. Well, okay, Chow variety of points. So you remember more information than that, but it is true that Hilb an splits as disjoint union by cardinality in pieces that I'm going to call Hilb d an. Now, this Hilbert scheme is a very interesting scheme, but it's also quite kind of intractable from a geometric point of view. Let me mention only one, just one property of it, which is a theorem due to Joachim Jelisiejew in 2018, I believe. Hilb A16 satisfies Murphy's law for singularities. What does this mean? Well, it means that every singularity type is a retract of a singularity in Hilb A16. If you think about it for a second, well, of course, this Hilb is not quasi-compact, so there is space for a lot of singularities, but it means that it has some really bad singularities. So trying to give a local study of Hilb is essentially impossible. And the goal, the first goal, so is, as homotopy theorist, is describe the motivic homotopy type of Hilb an. Well, this is not going to be really possible, again, but we can try to approach it a little bit better. We're going to study a simplified version, which is an in scheme, Hilb A infinity, which is just the, well, let me write it as the union n of Hilb an. So we are allowing families of points in affine spaces of arbitrarily big dimension, where here the union is given by embedding an in an plus 1 just by adding a 0. Sorry, at the end, the last coordinate. Oh, I forgot to mention, sorry, this work is joined with Marc Hoyois, Joachim Jelisiejew, and Burt Totaro. Maria Yakerson, of course. Yeah, she's always the last one, but we shouldn't forget her. Okay. Okay, so our goal is to describe the motivic homotopy type of Hilb an. That's impossible. So let's, well, easier goal, describe the motivic homotopy type of Hilb A infinity. So why is this easier? Well, the first reason why this is easier is that we are embedding our points into a big affine space, into an affine space of infinite dimension. And if we remember classical topology, this datum of an embedding into an infinite dimensional affine space is typically not an information. And so let me start with this proposition. So we have a map from Hilb A infinity to the stack that already showed up in the last talk of finite flat algebras. And this is a motivic equivalence. In fact, we're going to show that it's already an A1 equivalence. This is not a very surprising result, but since we're going to have people in the audience that maybe have never seen this kind of argument before, let me give it. So remember that we have LA1, which goes from all presheaves over smooth schemes over S to A1 invariant presheaves. This is the A1 localization, is the left adjoint to the inclusion. Is given by sending a presheaf F to the presheaf obtained, the way you can imagine, where delta n is the, well, let me put on S, is the algebraic simplex. Okay, so we have this localization. We can get it in sort of the most naive way possible. This is not true for the motivic localization, for the left adjoint to the inclusion of motivic spaces, but we're going to show that it is an even equivalence. It is that the map LA1 from Hilb A infinity to LA1 of finite flat is an equivalence. And in fact, we are going to show something even stronger. We're going to show that before, so this is a map of geometric realizations of these schemes, to the delta n that I wrote here is equivalent to, sorry, this is also, we can also write it like this.
Denis, there's a question by Nanjun.
Sure.
Absolute value mean in the F in the LA1 is absolute value. What does that mean?
Oh, sorry, no, that's not an absolute value. Sorry, that's okay. Let me spell it out a little bit further. So this is a functor from the simplicial category to spaces, sending n in f of whatever our argument is. Let's call it x.
You mean geometric realization?
Sorry, yeah, and taking the colimit. This is geometrically realized.
Okay.
So we want to show that this map between geometric realization is an equivalence, and we're going to show that Hilb A infinity delta n, sorry, delta dot of simplicial spaces is a confibration, a trivial confibration, sorry. And this, of course, will imply that it's an equivalence on geometric realizations. And what it boils down to it is going to be very simple. When you unwrap what everything means, it boils down to this very simple statement. So suppose we have a diagram like this. Where A is a ring and I is some finitely generated ideal. You should think of A as delta n and A mod I as the closed subscheme given by the boundary. So let me say this is the boundary. Then we can construct a lift. Okay. Well, maybe I should go faster, but this is a very explicit thing. This means that we have some A algebra B. We have an object here is given by some A algebra B. And a map, a lift, sorry, and this composite is given by B mod I, and the fact that this composite, sorry, You cannot see what I'm pointing at. It's B mod I. And giving an embedding into Hilb, giving a map to Hilb by infinity is the same thing as saying that it's a closed subscheme of some big affine space. So it ends up being the surjection to B mod I. I'm sorry, not to K, but to A mod I. And we have AX. So what we need to do is to find a surjection that make this diagram commute, so to speak. Well, okay. You can add a bunch of variables that go to 0. I guess that's the point. Essentially, okay, sorry. What I want to say is boils down to I can extend every set of generators of B mod I to a set generators of B by adding generators in IB. Okay, when you unwrap all the algebraic fact, and this is a very elementary and very obvious algebraic fact. Okay, and so this proves that the embedding into A infinity is constructible. Okay, I'm not sure I'm going to give any proof in this much detail. So are there any further questions? Any questions, sorry, about this proof? No? Okay. So our goal has become study the motivic homotopy type of finite flat. And there is and I'm going to describe the following theorem. The map from vect to finite flat that sends V to, let's say, K is our to the square zero extension, is an equivalence, is a motivic equivalence, sorry, after group completion. Okay, what does this mean? So first of all, we have this map that sends a vector space to its square zero extension. But in order to speak about group completion, I need to have an operation. So here I just take direct sum, and here I take, no, sorry. Okay, sorry, I described the wrong map. The forgetful map is an equivalence. Sorry, forgetful map, finite flat to vect is a motivic equivalence after group completion. So here I have the direct sum, and here I have the direct product. And hopefully now this is a map of groups. But, okay. Okay, so in fact, what happens is that this is a motivic equivalence on the nose. There is a very simple motivic, there is a very simple inverse using the square zero extension that I'm going to describe in a while. But I want to explain the proof of this theorem because we're going to need this technique to study the Hermitian case that I want to talk later. Okay.
Sorry, don't you use the disjoint union on the left?
Yes. I'm saying, okay, this is the categorical product of finite flat algebras. Sorry, that is the disjoint union of finite flat schemes, the coproduct.
Okay.
Ooh. Can you read when I write in green?
Not much. It's also not green. Wait, you.
It was supposed to be green, but okay, let me make it blue. It should be.
That's better.
It's supposed to be green. Sorry. Okay, there is something in the chat. It's like yellow. Okay, I'm going to come out and say I'm colorblind, but I also think that Zoom is doing some color distortion here. So this is blue, I think. Okay. So, okay, this is the theorem I want to talk about. And the idea is going to be the following. So is the statement of the theorem clear? Yes? Okay. Okay. The idea is going to be the following. We're going to study an auxiliary stack, finite flat marked. This is the stack of K algebras, sorry, of pairs, let's say AE, where A is a K algebra and E is an augmentation. We like to call it the stack of pointed points, if you want. Well, I like to call it. I don't know if the other people just humor me, because there are points together with a marked point, which I wanted to denote with a color, but now I'm not sure. Maybe red? Is red visible? Yeah. Okay, so a stack of pointed points. This, as it's known, classically, is naturally equivalent to the stack of non-unital finite flat algebras. So this is corresponding A comma E to the kernel of E, to just the augmentation ideal. And the inverse is going to send E to K plus, sorry, I to K plus I. Okay. Okay. Why are we studying this auxiliary stack? Because there is a very nice remark that says that the forgetful map from finite flat marked to vect, sorry, not marked, non-unital, is A1 equivalence. So this stack is in some sense easy to understand. I'm going to do the proof. And the intuition, so let's say intuition is that the inverse, well, that's not intuition, but the inverse is the map sending vect to algebras with zero multiplication. I said I'm going to use blue. And for these, I clearly need non-unital algebras, right? There is, if I have a unit, I cannot have zero multiplication. And the homotopy is basically going by doing a straight line homotopy of the multiplication with the zero multiplication. So we clearly have that the map from vect to finite flat to vect is the identity. but the map going this way is replacing the multiplication by the zero multiplication. So A to A with zero multiplication. So to make it homotopic to the identity, we need a homotopy. So a map from finite flat nu K to finite flat nu K brackets T over A1 of K. That sort of straight lines are a multiplication to zero, and that's going to just be sending A to this ideal. Concretely, this is sending A to the algebra A brackets T with multiplication A times special times B is just T times the old multiplication. Okay, so it's clear that when T is 1, we get the original algebra, and when T is 0, we get the zero multiplication. So that's an equivalence. Okay. We understand finite flat marked. We want to understand, so finite flat. And here is why we can do this only up to group completion. So the first remark is we construct a mapping telescope to do so. So let me draw a diagram here that might be useful to understand what we are going to do. We have this sequence of stacks where the maps are add one trivial line bundle to our vector bundles, and we have this equivalence here is the inverse of the previous equivalence, and this is the map sending V to the square zero extension. And I'm not going to belabor on what this map is. No, sorry. No, I don't want this map. Again, I keep doing things in the wrong order. I have the forgetful map. That's the map I want. And I have finite flat marked. And I have forget again. And here are just adding a disjoint point. But you need to be careful because this point I'm adding is not marked in the bottom row. I'm adding a point, so this operation is taking a pointed point. No, it's in red. And the operation is just copy. No. Copy it. No. Oof. Oof. What is copy? Oh, this is copy. Finally. And I'm just adding a special point here, disjoint from all the others. And I know that these composites here are A1 equivalences. So I'm going to, in particular, they are motivic equivalences. And I can pass to the limit and I get vet infinity, which is the group completion of vect. here I have finite flat marked infinity, whatever that is. And here I have finite flat infinity, which I'm going to claim in a second is the group completion of finite flat, even if it's not completely obvious. And I know that the composite is an equivalence. I'm going to claim that this arrow I'm marking in blue here is an equivalence as well. And this will allow us to say that the forgetful map here, I'm marking in orange, I guess, is an equivalence.
You mean A1 equivalences?
I mean motivic equivalence. I think everything is an A1 equivalence actually, but I don't want to pay attention to it right now. I think everything is an A1 equivalence actually, but we only care about the statement as some motivic equivalence. So, okay. These in particular will imply that finite flat infinity is also the group completion of finite flat, because the mapping telescope is not always the group completion, which might become a surprise to people that are not used to homotopy theory. But the issue is that is the classical issue that you have when you try to do algebraic K-theory. So if you have an infinity group, or more generally an H group even, the pi1 needs to be abelian. And in mapping telescope, the pi1 is not always abelian. In particular, the issue is that the map concretely, the issue is that the map from finite flat infinity to finite flat infinity might not be an equivalence. But since we know that it's going to be an equivalence for vect infinity, and the claim implies that finite flat infinity is also equivalent to vect infinity, then this is also going to be an equivalence. So, but it is going to be, because it is vect infinity. Okay. Okay. So now it's time to prove the claim. So this was an aside. So you might think, oh, this claim is obvious, right? Because I can easily construct a map that's an inverse by constructing arrows like this that add a marked point. So the first idea is you have finite flat plus k, finite flat marked, They have obvious maps here that add a marked point. But there is a problem. And what is the problem here? The problem is that the diagram does not commute. So this idea, just to be clear, this is going to send A to A plus K, subjecting to K. This is this map epsilon. If the diagram did commute, this would give indeed an inverse in the colimit. But there is an easy solution for this. Yes, the diagram does commute up to homotopy. Okay, it's not an easy solution, but we are doing homotopy theory. So our goal is not going to prove that this is an equivalence of stacks on the nose, and on some level we don't expect it to be. But we are allowed to prove, to change things up to homotopy. So let's have a look. So the bottom triangle here, that I'm going to, even if you can see it well, you should be able to see at least some kind of vague grayish thing. The bottom triangle does commute on the nose because I'm just adding a point. No, sorry. Wait. Oof. No. Yeah. Of course, it went this way. No. Yes. So sorry, it went the other way around. This triangle does commute on the nose because I'm adding a marked point and then I'm forgetting that's the same thing as adding a point. But this other triangle, this blue triangle, does not commute. Because going in one direction, so I start with a set of points, direction, sorry, it's at a set with a marked point. When one direction is just adding up this joint point, and the other direction is adding a point, but adding a point and marking it there. So this is a problem. It doesn't commute, but there is a homotopy that allows us to make it commute. And that's what we call the bank robbery homotopy. Now I'm terribly late with time, and I want to say something about the Domitian story, because this is kind of a bank robbery homotopy works like this. It's taking the, so we are in our setting, we have our point, we have a marked point, and we take this point and we make it collapse to the marked point, and we get a double point here, or a triple point, through a straight line, and then it goes back. Sorry, let me paste it. Okay. Bring in the marking with himself. So there is an A1 family following this line, and there is an A1 family following this line. And okay, I'm kind of lying because you need to check more things. You need to check that this homotopy is somehow compatible with the telescope, but it is. This implies that the map from flat marked is equivalent. Okay. Are there any questions?
Why is it called bank robbery?
Oh, yeah, thank you. Forgot to mention it because we decided the marked point originally was the bank and the marking was the money. And the point that we added is the robber.
Sasha also raised their hand. I don't know if they just asked the question.
I think they are the one that just asked this question.
Okay.
Are you? Sasha?
Is it your way to pronounce Shahar?
Ah, okay, that's me.
Sorry.
So these points that move around, here you consider the model where you are having an ambient, or I should think of it as like,
No.
where those these points move?
Okay, concretely, if you have an augmented algebra like this, the homotopy is sending this pair to, well, there are two homotopies, the two homotopies I described. It's not embedded, it's T epsilon minus epsilon square. No, oof. Sorry. Okay. Here it is. There are two homotopies mapping like this, but they differ on the choice. Of this map. And as you can see, there is no need of having an embedding. This is just gluing. So this family is just the family of 2 points colliding together.
Oh, okay, thank you very much.
So I'm drawing, there is no way of drawing it in a way that's not embedded, of course, but okay. And okay, so these allow us to say that the map from the forgetful map from faithfully flat group completed to vect group completed was in fact a motivic equivalence. Since this is just faithfully flat infinity and this is vect infinity, as I argued before, and we had this, well, we had this triangle here. So we get as a corollary the statement that Maria was talking about before. KGL is just sigma infinity framed, well, sigma infinity framed of vect group completed, but so it's necessarily sigma infinity framed of finite flat, where the group completion is actually not important because sigma infinity framed inverts group completion. So we can interpret KGL as the free cohomology theory with finite flat transfers. Although that's not literally as true as we want for the issue that was discussed in the previous talk, or mentioned at least in the previous talk. That the lack of a cancellation theorem for finite flat.
Dennis?
Yes?
So is it not true or is it not known to be true?
It's not known. I mean, I think we expect it to be true.
Okay, thank you.
I don't know, but okay. This thing, but every time I stop writing, it stops the share screen, is annoying. Okay. Sorry, this took longer than I thought. It was less clear than I thought, but okay, the upshot was KGL sigma infinity framed of finite flat. And in particular, Hilb A infinity has the homotopy type of a Grassmannian. And let me mention that I said the statement up to group completion, but in fact they're true without group completion. There is a much simpler proof that I didn't give here in the interest of time. But I want to, because I want to dedicate some time to talk about the following question. How much time do I have? I have half an hour, right? Yes? No?
Yes.
So what about KQ? So what is KQ? KQ is Hermitian K-theory. And as you might or might not know, there are issues when Hermitian K-theory is not, when 2 is not invertible, but I'm not going to assume it, because one of the cool things I think we can get out of this is that the story works perfectly well even when 2 is not invertible. Although not all the answers are as clean as we want. So remember, Hermitian K-theory is defined as the group completion of vector bundles together with a symmetric bilinear form, non-degenerate symmetric bilinear form. So these are pairs VB, where B is a non-degenerate symmetric bilinear form. Okay, the sum is the orthogonal sum. And we want to figure out what kind of transfers does this Hermitian K-theory have. A priori, note that this is not even a motivic space, but in fact, there is a theorem by Schlichting that says that vect sim group is a motivic space, at least for quasi-projective varieties. That is, it has a Jelisiejew that is a one invariant. And
Denis, are you actually working with affine varieties here, no? Otherwise,
let's work with affine varieties. Yeah, okay, let's say affine varieties, but you only need enough vector bundles for the statement to make sense and be true. Although the proof is very complicated, and as I mentioned, there is a simplification. Let's move forward.
I think I agree with Mark that this will not be true unless you assume affine.
What do you mean? Oh no, right. Sorry, I should be a bit careful. I understand the problem now. The problem is what I mean with group complete. Here I mean group complete as sheaves. That is, you group complete and then you sheafify.
Sure. Okay.
So yeah, let's say affine varieties, just to be clear. So that we then don't need to sheafify because it's split already. Yeah, sorry. Okay, so what we need is some kind of algebras equipped that come equipped with a symmetric bilinear form, because we want to get a forgetful map to vect sim now, not to vect anymore. And the answer is finite oriented Gorenstein algebras. So what are these? So let me define. So let me define it like this. So a finite flat K algebra is Gorenstein if Hom K linear to A is a line bundle. It's an invertible A module. This is probably should better called flat families of Gorenstein algebras, because this is coincides with the classical definition only when K is a field. But for brevity, I'm just going to call them Gorenstein K algebras. And for those that might have seen this before, this is also the same thing as the dualizing complex. In the finite case. That's not true in general, but for finite flat algebras, this is the case. And so a finite flat Gorenstein algebra, Gorenstein K algebra A is oriented if there exists phi from K A K bases. That is, if we can trivialize this line bundle. Note, so making a remark, which is really the crucial remark of this whole story, a K-linear map is an orientation if and only if the bilinear form be phi x comma y f of x times y is non-degenerate. That is, it induces an isomorphism with the dual. Because the map that is, if the map from K, induced map home to home AK is an isomorphism, i.e. Okay, so so we can form a stack of oriented Farn-Gorenstein algebras that sends K to the groupoid of pairs A comma phi, and this clearly has a forgetful map to the stack of vector spaces with a symmetric bilinear form, non-degenerate symmetric bilinear form. And now the theorem I can talk about is that this map is a motivic equivalence. Okay, so
Dennis,
yes,
after group completion.
After group completion, yes, sorry. You're right. We, contrary to the previous one, we don't know if this is going to be a motivic equivalence. Oh, even the previous one, I guess, wasn't a motivic equivalence after group completion. It's the inverse that was. Well, anyway, right, after group completion. So in order to prove this theorem, we're going to need, we're going to follow the footsteps of the previous one. So we're going to need marked. Oh, but before, okay, sorry, before I do that, actually, let me give you some examples of oriented Gorenstein algebras. So we can take the double point and take as an orientation that maps and sends A plus Bx into B. You see that the phi, in this case, is just going to be the classical hyperbolic plane. Yeah. More generally, suppose that VB is a vector bundle, is a vector space or whatever, with a symmetric bilinear form. We can form K of x mod x squared phi with phi A plus Bx. B is still B, but now I need to tell you what the multiplication is. Oh, sorry. Where the multiplication is essentially going to tell you that K of x mod x squared is a subalgebra. V is almost square zero. Except that there is a component x. So this is the Gorenstein equivalent of a square zero extension. And the underlying B sigma is going to be just VB plus the hyperbolic plane. Hyperbolic plane. Okay. And this example is actually important because, at least to me, it suggests what should be the correct notion of a marked Gorenstein algebra. So let me say, so A phi Gorenstein K algebra, finite, flat Gorenstein K algebra, an augmentation E from A to K is isotropic if the element X such that the X blank is E is isotropic. So remember, B phi was non-degenerate. So for every k-linear map, there is an element that represents it. And so we can ask that that element is isotropic, that is B phi phi of x comma x is 0, or equivalently, E of x is 0. And this turns out to be the correct notion. So let me mention the lemma. So you remember, before we had a very obvious lemma, I didn't even prove it, I just stated it, that augmented algebras were the same thing as non-unital algebras. Here we have a similar statement, but it's, oh, but I didn't define what non-unital is, but okay. Let me say the lemma and then I'll define the elements. Oriented non-unital times A1. Here it's going to be almost the same thing. We're going to have a notion of a non-unital algebra, but we're going to have to remember a little bit of indeterminacy, but it's not going to change the homotopy type. So what is a non-unital algebra? Well, okay. You know what, in the interest of time, I'm actually going to skip this, but I'm going to state a different proposition. That the map to augmented marked finite Gorenstein algebra described in the previous example is A1 homotopy equivalence. So this is the one sending BV to K of X mod X squared plus V phi, what I described before. And then I'm not sure I want to prove it in detail because this requires me to give you a lot of definitions, and I think I gave you enough definitions already. Are there any questions about this definition of marked Gorenstein algebra? No. Oh, there is a question in the chat. No, it wasn't a question. Okay. 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 So we can write exactly the same diagram as before. We have finite Gorenstein. Oh, sorry, the arrow of no.
Oh, sorry, maybe I have a question. In the proposition, do you mean that that's sort of without group completing?
Well, that actually makes no sense to ask it after group completing, because the right hand side doesn't have.
Oh, that's right. Yeah, yeah.
But actually, probably what I should have done. Okay. Okay. What I should have remarked, though, is that if you post-compose with vect sim, you get the add an hyperbolic space map.
Okay. Yeah, yeah.
Maybe this I should have remarked. Yeah, the problem with these marked stacks is that they don't have a, they're just a, so for example, in finite flat marked is just a finite flat module. At least for the structure. I mean, you could imagine to take the wedge, but that's not the kind of operation we are interested in right now, right?
Right.
We want. So we can draw the same diagram as before, and we know that this map is an equivalence at the level of mapping telescopes. So actually, we can take finite. Let me write the mapping telescopes. And sorry, I should tell you what these maps are. Well, okay, I'll tell you. Okay, let me draw the whole diagrams and then I'll explain who all the objects are. But the story is going to be exactly as before. This composite is going to be an equivalence because the inverse map is the map described in the previous proposition. And we're going to prove that this blue arrow here is an equivalence. Therefore, the red arrow here is also going to be an equivalence. So first of all, what are these transition maps? Instead of adding, so in vect sim, there is this lemma, I guess, which I might or may not prove. Vect sim infinity is A1 equivalent to the group completion, where vect sim infinity is obtained by, actually, I didn't give it a name, so let me just, where vect sim infinity is the mapping telescope for 0, 1, 1, 0. Now, I don't know if that is true without the A1 equivalence. I suspect it's not, but in any case, we are not interested in the question for the moment. because we were only working up to A1 equivalence anyway, or up to motivic equivalence even. So there is this simple lemma that, oh, I guess, no, okay, I should say when 2 is invertible, this is true without the A1 equivalence. Sorry. But when 2 is not invertible, we don't know if it's true or not without the A1 equivalence, but again, this is not a concern. So this object here is just at least A1 equivalent to vect infinity, to vect sim group completed. And what are these here? We are just adding a double point, a Gorenstein point, which is the first example I gave. And here we are adding a double unmarked point. So the augmentation factors through the first projection, as in the non-Gorenstein case, in the finite flat case. So we need bank robbery homotopy again. So let me draw the diagram bigger. So we have oriented marked. So this is plus k of x mod x squared plus k of x mod x squared. This is forget. This is forget. And we want to construct a map. Oh, sorry, I keep putting it in the wrong direction, but of course it needs to go this way. This map epsilon, and epsilon this way. A phi is going to be a plus k of x mod x squared, phi plus phi. Well, phi is actually let me call this psi, since I called phi the other one, and here e b plus cx. It's just b. So this is adding a disjoint double point with its Gorenstein structure and marking it. And as before, one of these obviously commutes. No, wait. Sorry. This one. One of these obviously commutes. This one. And this one doesn't obviously commute. Doesn't commute actually. But it does up to homotopy. Okay. And the homotopy works exactly as in the previous case. You collapse the double point, the two copies of the double point, paying attention to the orientations. So upshot, sigma infinity framed, okay, upshot, sorry, the map for Gorenstein oriented to vect sim is a motivic equivalence. Okay, up to after group completion. This in particular implies that vect sim has oriented Gorenstein transfers. This is a formal statement. Essentially, if Gorenstein R is, no, at least up to group, well, okay, let me group completed it. This is actually true also without group completion, but so in particular, it has framed symptomic transfers. Because if A over K is symptomic, omega A over K is the determinant of the relative cotangent complex. So if you have a trivialization of the relative cotangent complex, you also get a trivialization of the dualizing complex. So it makes sense to define KQ sigma infinity framed of vect sim group complete. And now this recovers very effective Hermitian K theory when 2 is invertible. And we hope it does so also when 2 is not invertible. But we don't have a proof yet. And in fact, there isn't, as of now, a definition of a motivic Hermitian K theory spectrum when 2 is not invertible, although one will appear due to some forthcoming work of myself and Jonathan Harpas and a bunch of other people that we are essentially read with. Let me say all of them: Battista Calmesse, Emanuele Dotto, Jonathan Harpas, Fabian Heberseit, Markus Land, Christian Moy, Thomas Nikolaus, and Wolfgang Steiner. We are going to provide a whole framework to do Hermitian K theory when 2 is not invertible. And there's, at least my hope, is that this KQ will be effective Hermitian K theory when 2 is not invertible. But we don't have a proof yet. And it is possible that it is actually false. So, okay. Are there any questions about this? If not, I think I'm running out of time, actually.
We will all thank you if you unmute us.
I mean, I'm not supposed to.
Are you finished or?
Yeah, I mean, I'm waiting if there are questions, but if there aren't, let's say.
So, okay, I'll unmute everybody so we can thank Denis. All right, sorry, I think someone started asking a question. So you should unmute yourself again.
Hey, Denis. Is there an analog of this for like symplectic forms instead of symmetric? I think you're muted
Dennis, you
still,
also
by
need
the
to
way.
unmute yourself.
I'm not muted. You should be able to hear me.
Okay, I can hear you now.
Okay. You mean of the Gorenstein things? No, not that I know of right now. So symplectic forms are supposed to be a shift of Hermitian K theory, right? The 2-1 shift, I think, or the 4. No, the 2-1 shift of Hermitian K theory, or the 4-2 shift. Oh,
It's the 4-2 shift.
The 4-2 shift, yeah. And no, but I don't have an analog of Gorenstein rings for. Okay, well, I'm going to stop trying to share the screen while I talk. No, I don't have an analog of Gorenstein rings for symplectic forms. I'm not even sure what it would be. I mean, we want some kind of maps from A to the dualizing complex, but with a -1, I don't know how to. I have no, I don't have one.
Maybe one could think about graded algebras and then ask for a multiplication which is graded commutative.
Oh yeah, that's probably going to actually in some version. I don't know. Okay. So I see there is another question. So sorry, this is, I know this doesn't answer your question actually, but that's the best answer I have. I don't have a symplectic version of Gorenstein algebras.
Oh, no worries. Thanks anyways.
But since I'm here, let me actually, since I made me think about this, I actually have a further questions I want to ask that I don't have an answer for, is what is F-Gor without the orientation? It's the homotopy type of the stack F-Gor. This is something that has frame transfers, so it should compute some kind of oriented version of KQ. And there are two natural candidates. I think there is KGL, that we recover KGL again, or that we recover the homotopy fixed points of KGL by the natural C2 action. And I don't know what the answer is. So I've tried to think about it for a while, but I don't have. Okay. So I think that there is another question about what is the mapping telescope. Sorry. If I have an object here with an endomorphism, the mapping telescope is just the colimit of F, like this. And yeah, that's the same meaning as in chromatic homotopy theory, but there is the multiplication by a VN map. Here for me was just adding either a line bundle or this K of X mod X square, or the hyperbolic plane or whatever. So I don't know if that answers the question that was in chat.
This is a little far out, but what would you imagine saying about the Hilbert scheme of higher dimensional, varieties, so to speak, or schemes?
The Hilbert scheme of, I don't know, because this is in a sense discarding the variety by the proposition I presented at the beginning. The embedding into A infinity is in fact like no data whatsoever. We are embedding into A infinity exactly to forget the data of an embedding at a finite AN. If I embed into some other variety, that's going to give some data.
No, sorry, I meant what about, basically the space of all, say, n-dimensional schemes as opposed to the space of all zero-dimensional schemes? Maybe they should be proper,
In that sense. So in the case of MGL, what you actually get conjecturally are d-loopings of MGL, like the higher spaces. Well, okay, that's not literally true. We also need to include derived schemes for that to be true, for that to be conjecturally true, if I recall correctly.
The de-looping of MGL is not conjectural, actually. The conjectural part is in the negative.
The looping is the looping, you're right. I always get the directions wrong. Sorry. So there is this conjecture, I think, that says that omega infinity of omega n MGL is sigma infinity framed of proper quasi-smooth. Is it, do you need proper? Yeah. Proper quasi-smooth schemes of dimension n. Only you need derived schemes for this to be true. So one could imagine to try to do the same thing with KGL. But If that was a conjecture, this I don't even know what it is. It's a wild dream, perhaps, a random guess. You could, I mean, this is a conjecture. This is even some kind of n-dimensional proper flat derived schemes. I mean, that's that's the guess but I don't want to commit myself to this. This is the guess that comes natural thinking of this other conjecture, which is actually true for negative n, I believe. But for positive n, which is of course in some sense the more geometrically interesting one, it's open. And that's probably you need some kind of other adjectives. I mean, proper flats seem a bit too general to me, as I see it written down.
And by the way, we don't know it for negative n, we know it for finite quasi-smooth.
Is it finite different from proper for negative n?
We don't know that it's the same, we expect.
Okay. Thank you.
As far as I understand.
Yeah. So I don't know if this is a reasonable conjecture, but that's what I would say.
Yeah, thanks.
Okay, are there any other questions? All right, so I don't see any, so I'll unmute everyone again and we can thank Denis.
I'll stop the recording now.